In this video, we're going to be talking about exponential functions, but then also coming back around and reviewing two of the types of functions that you've learned earlier on in this year, and that is linear functions and quadratic functions. But before we get into this, there's a couple of just skills, some concepts that I want to review with you because they're things that we're going to need to use in the lesson. So let's look at this warm-up. So find the slope and the y-intercept of the line that passes through 420 and 2024. So let's see if you guys remember how to find slope. There's a formula that you learned earlier on in the year, last semester. Slope we represent with m, and you might have an idea. I'm sure some of you might want to say y equals mx plus b, because that most likely you for sure know that part. But that's not completely what we need. Slope is just m. We will use y equals mx plus b perhaps, but not in this case. To find slope, the formula is y2 minus y1 over x2 minus x1. So in this example, 4 would be x1, 20 would be y1, this 20 would be x2, and 24 would be y2. So I'm going to replace in my formula y2 with 24 and y1 with 20. And I'm going to replace x2 with 20 and x1 with 4. And then simplify. 24 minus 20 is 4. And 20 minus 4 is 16. Generally, once we do this, we want to look and see if anything simplifies. Can I reduce this fraction of 4/16 or 4 over 16? I can, because I can divide both the top and bottom number by 4. 4 divided by 4 is 1. 16 divided by 4 is 4. So the slope between these 2 points is 1/4. So we did that part. Now let's talk about the y-intercept. How do we find the y-intercept? Well, that's where this y equals mx plus b is going to come in handy. Because in this form, y equals mx plus b, the y-intercept is b. So I have slope, I can plug that in for m, and I have 2 points to choose from to plug in for x and y. If I do that, all I'll have left over is b, and I can solve for it. I'm going to choose this first point, 420, because it's smaller numbers. So in y equals mx plus b, I'm going to replace y with 20, m with the slope that I found, which was 1/4, x with 4, and then plus b. Now, this works out nicely because this right here, 1/4 times 4, all that is 1. If I have 4/4, that is equal to 1. Solve for b by subtracting 1 from both sides, and I get 19. So 19 is your y-intercept, and 1/4 is your slope. Okay? So that was from a long time ago, but hopefully some of this looked familiar to you. Let's look at the next one, because this is what you did just a couple of days ago. It says the population of a town is decreasing at a rate of 1.8% per year. In 1990, there were 4,600 people. So, number 2 wants us to write an exponential decay function to model the situation. If you remember, that formula looks like this. And it's minus r because we are decreasing or decaying. So, what goes in for p is the initial amount, which they tell us is 4,600. Actually, I'm going to run out of room, so let me move this down. So 4,600, and then 1 minus my rate. Now remember, 1.8% is not 1.8 when I plug it in. I need to move the decimal place over twice, and that makes 0.18 to the t. Now that is my model. That's my formula. Number 3 then asks us to find a number answer. So they want us to find the population in 2010. Now, am I going to plug in 2010 for t? No, because it starts in 1990. So how many years have passed if it's 2010 and it started in 1990? Well, that's 20 years. So we're going to plug in 20 for t. So we put that into the calculator and see what we get. Now remember, when you do this, you can do this all at the same time. As long as you put it in like you see it here, the way it's written. So if you do that correctly, I believe you should get 3,337.88. Now, is this a situation where the 0.88 makes sense, or does it not make sense? Well, in this scenario, we're talking about people. So we can't have 0.88 of a person. So I change this round to the nearest whole number, which should be 3,338 people. Okay, so that's what you guys did a couple days ago and just took a quiz over just recently. So in today's lesson, what we're going to be focusing on is identifying when we see a table or a graph or some kind of scenario, identifying whether it is a linear function, quadratic, or exponential. These are the 3 big functions that you've learned this year in Algebra 1. They're like the main ideas of Algebra 1. If you guys take Algebra 2, you're going to dive a little bit deeper into these 3 different functions. So go ahead and go to the next page of your notes. And because I'm talking about this on a video, I'm actually going to skip this first page of showing you or talking you through how to use your calculator. If you are curious at learning how to use your calculator for what we're doing today and graphing points in a table to see what shape they make, look at these notes on this page, because it steps you through step by step everything you would need to do to look at the shape of the points on your graphing calculator. But with what we're doing today, we do not necessarily need the graphing calculator. So we're going to go on to the next page, and we're going to talk about how do we identify whether a relationship or a model is linear, quadratic, or exponential. So before we look at these tables and these pictures, because just by looking at the picture, I'm sure you could probably identify which one's which. But I want to talk about what kind of patterns should we expect to see in a table for each one of these types of functions. So let's talk about linear. So with a linear function, we should expect to see that you add or subtract by the same number. So as you look at your output values or your y values, it will be linear if you are adding or subtracting the same number each time. Now a quadratic, you may or may not remember this, but they need to have the same second difference. And I'll remind you of what that looks like. Oops, first need to spell difference correctly. And then also you might see the points increase and then decrease, or you might see them decrease and then increase. Regardless, you should see a change kind of in direction of the pattern in the numbers. And again, I'll show you when we look at these tables. And then exponential, that's what we've been working on these past couple of weeks, that we multiply by the same number each time. So that's how you, looking at the numbers in the table, that's how you determine which model is being shown. So let's look at this first table. Now you have a graph here. The points are plotted, so you might already have an idea of what this is. But I want to talk about what I wrote in black below each function to show you why by looking at the table I can also determine what type of function we're looking at. So something that I notice, I'm increasing and then I start decreasing. So going from here to here, my numbers increase, but then from here to here, my numbers decrease. That's an indication of a quadratic function. And if you look, what shape is it making? It's making a U. So quadratic functions, we should expect some kind of a U shape. Linear functions, we should expect, of course, a line. And then exponential, maybe a J kind of shape, where it's got a tail and then increases upward. So by the shape and by the fact that my values are increasing and then decreasing, this gives me very solid reasoning to believe that this is quadratic. And then let's look at this next one. So I do notice that with each of these numbers, as I keep looking, I'm decreasing. So I'm getting smaller and smaller. So let's say if I didn't have the picture below to help me, let's say I was trying to see if this was linear. To go from 16 to 8, that's minus 8. To go from 8 to 4, that's minus 4. So I am not subtracting by the same number each time. Now let's look at, or let's talk about multiplying. What can you multiply 16 by to get 8? Well, 8 is 1/2 of 16. So 16 times 1/2 is 8. Let's see if that keeps working. Half of 8, yep, is 4, and half of 4 is 2. Bingo. So I'm multiplying by 1/2 each time. So this must be exponential. And if I look at the picture, I do have kind of a J shape, where this really wouldn't be a J, but I've got a flattened tail and then a part of the graph that's pointing upward. So let's look at the next one. This has to be linear, I would think, if we're trying to identify and we only have 3 choices. But let's make sure we understand why this is linear. Obviously the picture is in the shape of a line. But let's look at the table of values. To go from 170 to 161 to 153 to 144.5, I am constantly getting smaller or decreasing. So let's see what I would have to subtract from 70 to get 161.5. So I'm going to do in my calculator 170 minus 161.5. That's minus 8.5. So let's see if I do 161.5 minus 8.5, I get 153. See if I do that again, I get 144.5. So subtracting 8.5 each time gets me my next number. So we have very strong evidence to suggest that this table and this graph is an example of a linear function. Okay, so what we're doing in this lesson is just using the patterns in the table or the shape of the graph when we plot the values in the table to identify which type of function it is. So the reason why we do this is because scientists and a lot of people that use math in the real world, they gather data or information about what they're observing or what they're seeing. And they want to try and have some kind of way to generalize or model what it is that they're seeing. So by looking at how the numbers behave and how they are related to one another, they can determine what type of function is best going to model that data. So let's look at these, and we're going to look at the table and we're going to look at the graph and determine what type of model we have. So one of the things I want us to review is how to make a graph when we've got big numbers. So time is always our independent variable. So time is going to go along the bottom. Now all I have to do on time is go from 0 to 4. So I could use every little box as one, but that's going to make my graph really squished together. So what I'm going to do is I'm going to skip every other box. And so each one is worth 4. Now I could have skipped more if I wanted. And this time unit is in 8, says H. So I assume that means hours. So time in hours. Now, to figure out what I'm going to do on my vertical axis is I'm going to take this number and I'm going to divide it by the number of boxes that I have vertically. And that's going to help me see what do I need to increase by, or what do I need to make my scale on the vertical part of the axis. So I'm going to count the boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. I have 25 boxes. So I'm going to do 6,144 divided by 25. And I get 245. So what I'm going to do is I'm not going to go by 245s because that's going to be difficult to do that math in my head. I'm going to go by 250. So each box is going to represent 250. That's still a lot of boxes. That's still a lot of boxes to label. So if each box is worth 250, what's 2 boxes worth? 500. If 2 boxes are worth 500, what's 4 boxes worth? 1,000. So I'm actually going to count every 4th box. So this is 1,000. 1, 2, 3, 4. 2,000. 4 more. 1, 2, 3, 4. 3,000. 1, 2, 3, 4. 4,000. 1, 2, 3, 4. 5,000. 6,000. And so the very, very top edge of the box is worth 6,250. Okay, so again, the way I determined how to make my scale was I took the highest value on the table, divided it by the number of boxes that I had, and then I made a choice to use 250 as what each box is worth. And so then I didn't have to label each and every single one. I skipped 4 and just labeled thousands. So let's now plot some points. So the point 0, 24. This first box is worth 250. 0, 24 is almost pretty much just right at the very bottom corner. The next one, 196 is not going to be much higher because that 196 isn't even at 250 yet either. Then I've got 2 384. So 2 384 is going to be a little bit above the 250 mark. And then 3 1536. So I'm going to go to where 1500 should be, which should be about right here. And then 4 6144. So I'm going to go all the way up to 6,000 and a little bit above. So look how quickly that increases. Now I'm not going to connect these dots. I'm just looking to look at the shape of the dots. This increases quite dramatically, so I have strong evidence that this is an exponential function. Okay? So all we did here is plotted points, looked at the shape, and it looks exponential. Let's take a look at this next one. So my x values need to go to 50, and my y values need to go to 500. So let's see what we should put as our scale on the x-axis. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I have 20 boxes. So 50 divided by 20 is 2.5. Okay, so that means I could make each box worth 2.5, which is actually going to make it so that it's going to work out perfect, because if one box is worth 2.5, then two boxes, 2.5 plus 2.5 is 5. So I can label every second box and count by 5s. So that makes 50 at the very, very end. Okay, then I have to get up to 500 on the y-axis, and remember we counted 25 boxes on the last one. So 500 divided by 25 is 20. So that means I could make each box worth 20, and if each box is worth 20, I could skip every 2 and go by 40. Or how many 20s is there in a 100? 20, 40, 60, 80, 100. So I could count every 5 boxes, 2, 3, 4, 5, and that's out of 100. And that gets me perfectly what I need. That ended up working out very nicely. So now I'm going to plot these points. So I have the point 1, 10. So the point 1, 10 is, if each box is worth 20 vertically and each box is worth 2.5 horizontally, 110 is in that bottom left-hand corner, pretty close to it. The next point is 550. 550 would be halfway between 40 and 60. And then 20, 200. So 20, 200 would take me here. And then last, 50, 500. Take me all the way up here. So looking at that shape, it increases all the way through, but it doesn't curve. It looks like it's a straight line. So that would mean, if it's a straight line, that it is linear. So it is a linear function. Bingo. Okay, so not too bad. Took a little bit of time to put that graph together and plot those points, but it wasn't like we had to do any serious calculating or anything. Okay, so we used the graphs to determine whether it was linear, exponential, or quadratic. Here we're going to use the tables. So we're going to look for patterns. So remember, linear functions, we either add or subtract by the same thing. Quadratic, we should see increasing then decreasing, or decreasing and then increasing. And then exponential, we should see multiply by same number. So let's look at this first table. So we're looking for a pattern. So to go from 4 to 68, I'm increasing, 68 to 100, increasing, stay the same, and then decreasing. So I increase and then decrease. Our only function that does that is quadratic. So easy peasy. Next one. This looks like it might be a little bit more challenging, so let's see what we get. So going from 1,000 to 1,169.86, and keep going, keep going. It looks like we increase the whole time. So that means it either has to be linear or exponential. So we're going to test and see if I'm adding by something each time, and if so, it's linear, and if not, I'm going to see if we're multiplying by something each time. So to get from 1,000 to 1,169.86, the difference there is 169.86. So if I add 1,169, this number, plus 169.86, I get 1,339.7, so that's pretty close. So then let's see if I add it again. So 1,339.72 plus 169.86, I get 1,509.58. So it's not terribly far off, but it's not exactly the same number. So chances are this may not be what we want. So it could be linear because it's not too far off. And in real life, sometimes the numbers aren't perfect. Like I don't remember when you were doing line of best fit, sometimes the shape is somewhat linear, but the points don't fall exactly on the line. So now I'm going to see if we multiply by the same thing each time. Now to figure that out, I'm going to do the second number divided by the first. And when you do that, you get 1.16986. Because dividing by 1,000 moves the decimal place over 3 places. So I'm going to test and see if I multiply 1,169.86 by 1.16986, I get, check this out, I get 1,368.57. That is way closer to that value in the table than the linear was. It's only off by 1/10. So if I do that again, 1,368.67, this number, times 1.16986, I get 1601.15. Again, very, very close. So I got these numbers, or pretty close to it, by multiplying by this number each time. Now it's an ugly number, but it is a number that I multiplied by each time. So that makes this exponential. Okay? So last piece that we're going to add to this is writing the function, actually writing the function once we determine what type we're looking at. So if I look, here's general form of a linear, y equals mx plus b. We talked about that at the beginning. And you may have forgotten, but this is what the general quadratic looks like, ax squared plus bx plus c. And then this is generally what an exponential function looks like. So let's take a look at what they want us to do in example 3. It says use the data in the table to describe how the number of people changes. Then write a function that models the data. Use your function to predict the number of people who received the email after 1 week. All right, so let's look at the table. So going from 0 to 3 days and looking at the numbers here, looks like I am increasing the whole time. So that means it's either going to be linear or exponential. It can't be quadratic. And thank goodness, because writing a quadratic equation, that would be more complicated. So let's see. You guys might have an idea, could probably see, that going from 8 to 56, 56 to 392, I'm not adding the same number each time because the gap between the numbers is getting bigger and bigger. So chances are I'm multiplying. So to find that out, I'm going to do 56 divided by 8. That's 7. So I want to see if multiplying times 7 gets me each number. So let's do 56 times 7. And I do indeed get 392. Let's do 392 times 7. And I get 2,744. So multiplying times 7, that's the pattern. So that makes this an exponential. And if it's exponential, then I'm going to use this function. So let's talk about what that function is and where I'm going to fill in the numbers. The a is the initial value, or where it starts. The b is your rate, or what you're multiplying by. So both those pieces of information are nicely included in this table. What's the initial value? 8. That's where we start. What am I multiplying by? 7. So there's my function. Easy peasy. So the last piece of this, so we wrote a function that modeled the data. Then they want us to use the function to predict the number of people who receive the email after 1 week. So how many days are there in a week? 7. So we're going to plug in 7 for my exponent and see what we get. I bet we're going to get a ginormous number. Pretty big. I get 6,588,344. It's a pretty big number. Okay? So I would say probably the first part of this lesson shouldn't be too difficult because you guys are pretty good about identifying whether the shape is linear, exponential, or quadratic. And I've given you some tips for how to identify by looking at the table, whether it's linear, quadratic, or exponential. Maybe the part that you might need to think about and work on the most is the writing the function part. That's probably the toughest piece of this lesson. But your assignment for today is going to be 9-4, practice B. Okay? And then here pretty soon we're just going to be reviewing this chapter, testing over this chapter, and then reviewing for the semester final. So you guys are almost done. So Let's finish strong.